Hey everyone. So welcome to day 2 of Ohm's Law. This is 7.14. And as we want to get started, I would like to begin by just refreshing ourselves on what Ohm's Law is. So Ohm's Law, which we talked a little bit about yesterday, is a formula you can find in your reference table, which says that R is equal to V over I. Resistance is equal to voltage over the current. Now remember, we also talked about this triangle that helps us figure out the different forms that this formula can kind of take on. So we've got V equals I times R. We've got I is equal to V over R. But all three of these are really saying the same thing. They're just kind of reformatted a little bit. We're also going to talk today a little bit about series and parallel circuits, and I'm going to end up drawing them out for you in the next slide. But for now, these sets of formulas are on your reference table. And what I really need you to take away from this slide concretely is that there are just different formulas you have to use for series circuits versus parallel circuits. If that is what you walk away with from this slide, that's totally fine. That's all you really need to know. I'm going to try to explain conceptually why there's a difference here, but I'm not going to assess you on it. So again, if after the conceptual explanation you feel like you're not really understanding why they're different, that's totally okay. All I need you to know is I see series, I have to use this set of formulas. I see parallel, I have to use this set of formulas. So to help us better understand, I'm actually going to draw out a series and a parallel circuit. So let's start with a series circuit first. Remember that series means literally like in a series, like one right after the other. So let's say that I had two resistors in series. That means I'm going to have one resistor followed by another resistor, and the current as it goes through here is going to have to pass through both resistors no matter what. It's only got that one path to go through. This is the equivalent of like making, I like to think about this in terms of like thinking about having y'all run through a hallway. And let's say I'm having you run through a hallway that only has one straight path, and I'm sending like maybe 25 of you down one path or 20 of you down one path. So no matter what, if there's only one path for the hallway, 20 of you are going to start here, 20 of you are going to end here, and 20 of you are going to run through this resistor, and 20 of you are going to run through this resistor, because it's the only option that you have. You don't have any other pathways. But we know that for parallel circuits, the story is a little bit different. So I'm going to draw out a parallel circuit now with, again, two resistors. Parallel circuits, you can kind of ignore that. So we've got one resistor here. We've got one resistor here. Again, this is my R1, this is my R2. So now we've got the current, and again, it's maybe 20 of you that are running this way, running this way, running this way, and then we hit this point. And let's say that some of you end up running this way and complete the circuit that way. But some others of you decide to go a different route, and you go this way, and you complete the circuit this way. So now the current kind of branched off a little bit. That original 20 of you, maybe 5 of you went this way and 15 of you went that way, and you branched off a little bit. And that's going to result in different currents being felt across different resistors. So in this case, the 20 kids that were running through the hallway, there was 20 people running through this resistor and 20 people running through this resistor. So the current at each resistor had to be the same. That's what this formula is showing us, that the current at each resistor was the same. In this one, though, because we ended up splitting off, let's say we had 20 here, like 20 all along running the route here, but then for whatever reason, this resistor had less resistance, so it allowed more current to flow through. So 15 of you came this way, and 5 of you came this way, because you 5 are very lazy and didn't want to go all the way around. Well, now we know that to get the total current, we'd have to add up both of these, and that's how we'd get the 20 that we started with, and that's what this formula is showing us. That in parallel, we'd have to add up the individual currents being felt at each resistor. Now, the voltage. We know that the voltage overall is going to be, let's give it a number here. I'm going to say that the voltage here is 10 volts, and that's the battery, what the battery is providing to the entire circuit. Now here we know that to go through each resistor, there's going to have to be some work done on this current. And I know that work is very closely related to voltage. We've talked about this formula before. Voltage is equal to work over charge. So to get these charges to go through, we got to do some work on them, and that's going to require some amount of voltage. And because this current has to go through both resistors, it has to do that work on both resistors. And because of that, we can add up both of those voltage values to get our total voltage. The voltage felt at this resistor plus the voltage felt at this resistor add up to the total voltage. This is a little different, right? Because here, they don't have to do the, they don't actually have to go through both resistors. So instead of having to add them up, we can just say that the voltage felt here is the same as the voltage felt here. Let's think about why that makes sense. If we were to set up a proportion, right? Let's say that this resistor was had a resistance of 1 ohm. This resistor had a resistance of 3 ohms. So if we were to solve out for the individual voltage here, we'd say that the voltage is equal to I times R, which is equal to 15 times 1, or 15. If we were to solve out the voltage here, the second voltage is voltage 1, we'd say that it's going to be 3 times 5, again, to get 15. Now, why did that happen? Because first of all, this current doesn't have to have the work done on it to go through both resistors, because it's not going through both resistors. They're kind of splitting off. And also, it's going to be related to how much resistance you actually have. If you have more resistance, less current's going to get through. If you have less resistance, more current's going to get through. But either way, because it's a relationship, the voltage is going to be the same. And so that's what this is showing. It's not added up anymore. The voltage is the same at both points. Finally, here, this one is pretty straightforward for the resistance. You just kind of add them up. So let's say this resistance was, like we did here, 1 ohm, and this resistance was 3 ohms. Then the total resistance would be 1 plus 3 to get 4 ohms. It's a little different in parallel circuits, and it has to do with that kind of branching off. But to be honest with you, explaining the whole reason why it's 1 over the resistance in this case is just not worth our time. So I'm going to leave it at that. And again, if you're not super comfortable with what I walk through with the conceptual understanding here, that's totally okay. Just recognize that you need to be comfortable doing series circuits versus parallel circuits. Simple as that. Okay, so let's apply this to an example just so you have an idea of what I mean. The following series circuit has a potential difference of 9 volts. And I'm actually I deleted the photo for a reason, the picture. I wanted to practice like drawing it out with y'all just so you're comfortable drawing in circuits. So there are 3 resistors, and it says it's a series circuit. So we know we have to go one after the other. I'm going to pause the video here for a second, and I want you to try to draw it on your notebook. Try to draw out the series circuit. Okay, so remember that we're going to start with the battery. A series circuit means one after the other. So we have the first resistor here. We can draw the second resistor here. And we can draw the third resistor here. If you didn't draw that, if you drew like resistor, 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 or resistor, 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 that's totally fine too. As long as you're showing 3 and they're in series, you're totally fine. This is R1, I'm going to make this 4 ohms. This is R2, I'm going to make it 3 ohms. This is R3, I'm going to make it 9 ohms. And I'm told that my circuit has a potential difference of 9 volts. That is my voltage. Cool. And now I'm asked, what is the current of the circuit? So I want to find out what I is. Well, I know what my voltage is. It's 9 volts. I don't actually know what my equivalent R. That Req just means the total resistance is. But I can solve out for it. I can use the formula that I'm provided. I'm told that Req is equal to R1 plus R2 plus R3. So it's going to be 4 plus 3 plus 9 to get 16 ohms of resistance. And once I have the 16 ohms of resistance here, well, I don't know what I just did. There we go. Okay, once I have the 16 ohms of resistance here, I have an R, I have a V. I need to solve for an I. We can use our triangle again to help us solve that out. V, I, R. Well, if I'm solving for I, I can do I equals V over R. And remember, this was the first setup, this is the second setup. To give me 9 over 16 to get 0.56 amperes. And because it's a series circuit, that's my current at each one of my resistors. It's the same current, 0.56 amperes of current. I'm going to change this up a little bit now. It's going to be a very similar problem, but I'm actually going to remove a resistor. So again, I have a series circuit again, but this time instead of 3 resistors, I only have 2 of them. I want you to give it a shot, and I want you to try to draw this out in your notebook again. Try to draw out the resistor. So if you try to draw this out, the circuit I should say, not the resistor. If you try to draw out the circuit, you should have gotten something like this. And again, if you drew it like this instead, totally fine. If you drew it like this, totally fine. You got some artistic freedom there, as long as you're showing both resistors. And I'm just going to stick with this image because it's the one that I like the most. 4 ohms and 3 ohms. And again, it's 9 volts. So just know what we know about resistance and how it interacts with the formula that we've been working with thus far. So R equals V over I. How does decreasing this affect my I? Take a second and try to figure that out. Give me an answer. Okay. So let's actually try it. Whatever you decided, let's actually put it to the case by testing it out. So again, we have that the voltage is equal to 9 volts. We don't have a resistance yet. We can find it though. And we are solving for I, so we don't know it. So how do we solve for Req? Well, we have a formula right here. Req is going to be equal to 4 plus 3, which is 7 ohms. So we can tell that the resistance decreased. If resistance decreases, well, I'm going to be dividing that 9, but now I'm going to divide it by a much smaller number. And that 9 divided by 7, let me plug that into my calculator real quick. 9 divided by 7, that gives me 1.3 amperes. So we can see that if we decrease the resistance, we're actually going to increase my current. The current from before was 0.56 amperes. This one is 1.3. Sorry, this should say amperes, not ohms. Amperes. This is 1.3 amperes. So as I increase my resistance, my current decreases. If I decrease my resistance, then my current has to increase. It's an inverse relationship. We talked about this a little bit on the last one. Okay, so that's series circuits. Let's see how this is a little different in parallel. It's a little more involved, a little more difficult. A 9-volt battery is connected to a 4 ohm resistor and a 5 ohm resistor as shown in the diagram below. What is the current in the 5 ohm resistor? So, important takeaways here. First of all, this is one more series circuit. So, we're not yet talking about parallel. I actually want you guys to give this a shot. I'm not going to set you up at all for this. I want you to just kind of go straight through it. Try to solve out the current in the 5 ohm resistor. Okay, so if you try to solve this out, let's list our givens first, because we've already had the drawing done for us. We know that the voltage is equal to 9 volts. Now, we're told that it's connected to a 4 ohm resistor and a 5 ohm resistor. So, I don't know my resistance yet, but I can solve it out by just using my formula, right? The R1 plus R2. So that's going to be 4 plus 5 to give me 9 ohms. And I'm solving out for my current, because I don't know it. I equals V over R to get 9 over 9 to get 1 ampere. Simple as that. That's all you really need to be comfortable doing for series. And I will say that out of the two, the series calculations are way easier. And you'll see why in a second. Okay, now we're moving on to parallel circuits. And the reason parallel circuits get a little tricky is because of this funky looking equation. So let's read through the problem again. The following parallel circuit has a potential difference of 9 volts. So we know that that's an important value. There are 3 resistors with values of 4 ohms, 3 ohms, and 9 ohms. What is the current of the circuit? Now, key word here, parallel circuit. This is what highlights to me that I cannot use that easy series formula that I used earlier. So we're going to have to change things up a little bit. So let's start off with just listing our givens. We know that we have a voltage of 9 volts. We know we're trying to solve for I. We don't know it. And we also don't yet have an Req. But again, we can solve for it. But the formula looks a little funkier this time. It's not as straightforward as it was before. We have a 4 ohm resistor. We have a 3 ohm resistor. And we have a 9 ohm resistor. So, according to this formula, if we want to solve for 1 over Req, we have to do 1 over Req is equal to 1 over 4 plus 1 over 3 plus 1 over 9. Okay, so solving this out, I get that this is equal to 1 over 16. Okay, I'm going to pause for a second. What mistake did I make? Okay, so if you caught my mistake, and this is a very, very, very common mistake here, you can't actually add denominators like this. You can't just add 1/4 plus 1/3 plus 1/9. This is no good. This doesn't work like this. So I'm actually going to come back here and erase this away because this is not helpful at all for us. The only way to add these up, and this is why this kind of problem is so much more annoying, is to find a common denominator. Now, easiest way to find a common denominator, we don't need the smallest one, we don't need the simplest one, just take the two biggest numbers and multiply them. That's always going to give you a common denominator. So 4 times 9 is 36, the common denominator is 36, so I have to multiply each one of these to get 36. This becomes times 9, this becomes times 9, this becomes times 12, this becomes times 12, this becomes times 4, this becomes times 4. And that's going to give me 9 over 36 plus 12 over 36 plus 4 over 36, and that's going to give me 21 plus 4 is going to give me 25 over 36, and that's 1 over REQ. Now, next mistake a lot of people make, they stop here. They're like, all right, cool, 25 over 36, solve that number, I'm done. But that is not true, because that's not going to give you REQ. That's going to give you 1 over REQ. So the last step here is to cross multiply. We get 25 REQ is equal to 36. REQ is equal to 36 over 25, which is equal to 1.44 ohms. Now, that felt like a lot of work, I know, but we're actually still not done because we just solved out for the REQ, 1.44 ohms. We still have an I left to solve for. So let's solve it out. We know that I is equal to V over R, which is equal to 9 over 1.44, and that's going to give me 6.25 amperes. And that is my final answer, 6.25. Oops, 6.25 amperes. Okay. Now we're going to change this up again. We're going to make the same change that we made to the series circuit. I'm going to decrease by 1 resistor. So I've got... Okay. I've got a potential difference of 9 volts. Cool. So I know that my voltage is 9 volts. I've got 2 resistors, but I can't just add them up like I did in the series circuit. I have to do that funky math, so I'm not ready to do that yet. And I'm solving for current. So I've got 4 ohms. And I've got 3 ohms. Now, notice that I actually eliminated a resistor here. By eliminating a resistor, I actually give the current less options as to where to flow. So if I give it less options, how do you think that that's going to affect the resistance if I give the current less options to flow? Think about the example of the running through the hallway. If you have less paths to run through in the hallway, how does that affect your ability to get through the hallway? Take a second and answer that. So if I give you less paths to travel, your resistance is actually going to increase. So even though it may seem counterintuitive, in parallel circuits, removing a resistor actually increases my resistance. I have less paths, less options to travel through. So again, we can solve this out. Let's do 1 over REQ is equal to 1/4 plus 1/3, which is equal to 3/12 plus 4/12, which is equal to 7/12. And again, we can cross multiply here to get that 7 REQ equals 12. REQ equals 12 over 7, which is equal to 1.7 ohms. So if you remember, in the last problem where we had 3 resistors, the resistance was actually 1.44 ohms. So my resistance actually increased. I have less pathways to go through. I'm a little more restricted. I feel more resistance that way. Now I can solve out for the second portion of this. I I know that I is equal to V over R, which is equal to 9 over 1.7, which gives me 5.2 amperes. And again, let's think about that relationship between current and resistance. Increasing resistance means I have less current. Instead of the 6.25 amps that I had in the last problem, now I only have 5.2 amps. Okay, example number 6, I want you to give this a shot. You can do it in your notebook, wherever you need to do it, but I want you to give it a shot and calculate this out. If the parallel circuit to the left has a current of 2 amps, what is the potential difference of the circuit? Go ahead and give it a shot. Okay, let's go through it together. So if the parallel circuit to the left has a current of 2 amps, so the current is 2 amps. I equals 2 amps. So let's list that out. I equals 2 amps. We're being asked for voltage. We don't know it. And if we check our reference table, we should keep in mind that the voltage is going to be the same across all of my resistors. So the voltage is going to be whatever number we calculate out. We do need to find my resistance because I don't know it. Okay. 1 over Req is equal to 1 over 100 plus 1 over 200, which is going to be the same as if I multiply both of these by 2, so I can get the 200 on the bottom, 2 over 200 plus 1 over 200 to get 3 over 200. I cross multiply, I get that 3 Req is equal to 200. Divide both sides by 3, and I get that Req equals 66.7 ohms. Cool. Now we know what to do. I'm solving out for voltage this time so I can draw in my triangle, the Beer triangle. We've been using, that's not a triangle, we've been using a lot of the same solving for current, but now we're solving for voltage, so it's helpful to rewrite it. I know that my next formula is going to be V equals I times R, which is going to be equal to 2 times 66.7, and that is equal to 133.4. No, that's not the unit. V should be volts. Cool. That's honestly pretty much it. Again, if the conceptual was not clicking, that's okay. I presented it to you just to give you a chance to see it. But again, I'm not going to assess you on it. What I care most from today is you just be comfortable using the formulas. Simple as that. Again, if you have any questions, please feel free to text, reminder, email, and your practice is due Thursday at 11:59 a.m. Best of luck, people.